Lesson 3, Fleming's left-hand rule. Be careful, it is the left-hand rule because there is also a right-hand rule, which we'll see later on. This is the motor effect, which is the basis of all electric motors, which whether it's your toothbrush or any engine or electric car or anything. Okay, we know when a current passes through a wire, it induces a magnetic field. We know that if a magnetic field or north pole from one magnet is brought close to a south pole of another magnet, they attract, or if a north pole from one magnet is brought to a north pole of another magnet, they repel. So we get magnetic repulsion or attraction. The motor effect uses this effect. A wire is placed in between the poles of a permanent magnet. So when a current passes through that wire, the induced magnetism interacts with the magnetism of the permanent magnet, which we can see in this video clip here, which is in the lesson.
If you put this magnetic field in another magnetic field, it puts a force on the wire. This is known as the motor effect. To determine the direction of the force, you can use a handy trick called Fleming's left-hand rule. The way this works is by taking your left hand and making this shape with it. You then assign your first finger to the direction of the magnetic field, which is always north to south, your second finger to the direction of the current, and your thumb to the direction of the force. For example, in this case, Fleming's left-hand rule states that the force would act in this direction.
Okay, so that's a description of Fleming's left-hand rule, which is simply to describe the direction of this induced force caused by the induced current from the wire interacting with the permanent magnet it is placed between. Force is the thumb upwards in this case. The magnetic field, symbol B, is your first finger and the current is the second finger. So hold your left hand out, your thumb, first finger and second finger all at right angles to each other. If the current is represented by the second finger, line that up with the direction of the current in your wire. The first finger is lined up in the direction north to south. Therefore, the direction the wire will be forced to move is the direction your thumb is pointing. Okay, and the rules for this in terms of increasing the strength of the motor effect are the same for the electromagnetism. If you increase the size of the current passing through the wire, you increase the force. If you increase the size of the magnetic field, so use a larger magnetic field, so a larger magnet, you increase the force, or a longer piece of wire. This can be achieved by having the wire in a coil shape, or in fact in most real motors you have multiple coils to increase the effect. It wouldn't be physics if we had equations, so to describe the force of a magnetic field, it uses in this equation. Force is B, the magnetic flux density. That just means the strength of the magnet. I is the current and L is the length. The problems in Appendix A3, again, it's just like every other equation we ever use. Calculate the force, so you write down your equation, substitute in the numbers, so there's the length, there's the current, there's B, the magnetic field strength. Plug those numbers into the equation and away you go. Again, check SharePoint for the answers. And that is the motor effect. Thank you.